So we're going to be looking at Chapter 5, Irreversibilities that can be present in our systems. So one of the things that we're going to be calculating is the best theoretical performance for our systems. This is extremely important for our second law of thermodynamics, because we want to compare both the actual performance and the best theoretical performance. Sometimes we look at the best theoretical performance because, one, it's a little easier to calculate, and then we compare it to the actual. It gives us insight into how to improve the performance. We tend to evaluate the idealized process and then compare that to the actual. And the actual processes have these what we call irreversibilities. These irreversible, like when we talk about equilibrium, we talk about a process that's being reversible, can go in the forward and reverse direction. Something that has got irreversibilities in there. For example, on the next slide here, we have, like, for example, heat transfer, right? Heat always goes from something hot to something cold. It doesn't go in the reverse from cold to hot. You got unrestrained expansion of a gas. Spontaneous chemical reactions. One I could think of is a rusting, right? When metal rusts, it goes in one direction, but it's not reversible to go back to a nice metal afterwards. Spontaneous mixing, I showed that in our previous example of milk with coffee. And once it mixes, it won't go back to the separate states. You have friction. You have resistance in electrical currents and magnetization, and we also have inelastic deformation. So these are some irreversibilities that you might come across. So when we look at an actual process, and an actual process involves any on those lists, some naturally occurring ones, and these are things that we have to take into account when you look at your mechanisms in some industrial plants. So there's things that we want to try to improve or reduce these effects. So when we look at our processes here, we know in our system we have irreversibilities, and they can be present. So in our process, so they're present both in the system, they could be present in the surroundings, or in both. And so these are something that we need to consider. So a process is considered irreversible. It can only go in one direction, basically, if you have irreversibilities in both and or the system and or the surroundings. Okay? There's, because we know actual, not idealized, but actual processes have irreversibilities present. Okay, something that is set up to be reversible has no irreversibilities within the system and its surroundings. This is idealized, and this is the easiest thing to calculate, so we don't have to worry about reversibilities. But it's something that's how we get our maximum thermal performance or coefficients by being idealized, and then we compare it to what it actually is occurring. So when we look at our processes here, we have another term called internal reversible. So when we set up this type of reversibility, we have no irreversibilities in the system. So the system is completely reversible, but the surroundings is where those irreversibilities are present. So we're just moving all those irreversibilities to the surroundings, and we'll keep the system itself as a reversible process. Okay, and a lot of times when we look at an example of internal reversibility, that's that quasi-equilibrium. The quasi-equilibrium, remember, equilibrium, we're changing, for example, we're taking and compressing a piston, right? But we're doing it so slow, and we're changing the height of that piston so infinitesimal that each time it's basically reversible as we go down. But the irreversibilities are present in the surroundings, but not within the system. So if you want to think about that, let's look at our piston here. Right now we have liquid water sitting here in our piston. Okay, it's saturated at 100 degrees. So this is going to be changing from liquid to gas without changing temperature. So we're just doing, it's just a phase change. In our system, it's going to stay at constant temperature, 100 degrees. The surrounding gases are at 500 degrees. Okay, so we do have transfer of heat to the water from the outside, but we're letting this slowly go from liquid to vapor in a state of equilibrium states. We're not like putting all the heat in right all at once and all of a sudden it just completely changes. We're just infinitesimally letting it go just a little bit each time without changing the overall temperature until we get completely saturated vapor at 100 degrees Celsius. So this is an internal reversible process, but we're not changing the surroundings itself have irreversibilities in it. So this is a quasi-equilibrium. So again, just reiterating, the system has no internal irreversibilities, but they do exist in the surroundings. Okay? So for example, spontaneous heat transfer, right? Heat always goes from something hot to something warm. We talked about this before, but here, if we're looking at a Kelvin-Planck statement, and Kelvin-Planck statement, it's impossible to take all the heat from one heat source and convert it all completely to work. Okay, but in this process here, we have some work being done externally, right? Where the masses can easily go down, and so when we have transfer from one source, that's always, it can never be positive, because we have to, in order to get that mass back up, we have to apply work, and so that means putting work in, so that's negative, and there's irreversibilities present when it's negative. And then also, if we don't have any irreversibilities, our work is going to be zero, so the mass isn't going to move at all. So just think about that. And to remind us, right, and we also said this can never be positive if we have a single thermal reservoir. So to remind us of our Kelvin-Planck statement, it's impossible, right, to operate a system between just one thermal reservoir and have it completely turn to work. We cannot have 100% of the heat being transferred to work. That's just totally impossible. Okay, so keeping this in mind, we're going to remind you of our thermal efficiencies and our coefficients of performances here for a power cycle. And we're going to calculate thermal efficiency, which is, right, the heat in minus the heat out divided by the heat going in. And recall that this is going to be less than 100%. Okay, it's always going to be less than 100%. And then if we have a refrigeration or heat pump where we're putting work in, and so we're removing heat from a cold source and putting heat into a hot source, depending on if we have refrigeration or a heat pump. And if we look at the coefficients of performance here, the refrigeration cycle, you have heat coming in to the system from the cold source minus the heat going out of the hot source minus the heat going in, and then the heat going out into the hot source, and then also the net cycle. And these, remember, are usually greater than 1. So keeping these in mind, let's look at our Kelvin-Planck statement that we just talked about. And there are 3 conclusions that we can draw from our Kelvin-Planck statement. And this first one is just going to be with the power cycle. So we're going to be talking about the power cycle here and looking at thermal efficiencies, right? Thermal efficiencies, as I already mentioned, has to be less than 100%. And we have some corollaries here. If we have an irreversible power cycle and reversible power cycle, so if we're looking at this example here, if we're going from a high to a low temperature reservoir, and this is irreversible versus a system that is reversible, our thermal efficiency for the irreversible is always going to be less than a reversible system. Again, we're talking about a process that's reversible and irreversible. Now, if we're looking at and you can look at either one of these two, if our heat sources are the exact same two heat sources, and if I'm looking at a reversible process at going from two the same heat sources, the reversible process must be the same because it's going to contribute and take in the same amount of heat. So your thermal efficiency will be the same. Okay? Now, if we do this for a refrigeration or heat pump cycle, do the same thing as I mentioned already, right? The coefficient of performance, each of these has to be greater than 1. And beta is for our refrigeration, and the gamma is for a heat pump. So this one's for a heat pump, and this is for a refrigeration. Okay? So our irreversible refrigeration or heat pump, it's always going to, if we have irreversibilities present, it's always going to be less than our reversible process, no matter if we're talking about refrigeration or a heat pump. So this is always going to, if there's irreversibilities present, it's going to be less. The coefficient of performance will be less. And the same with the last one. If we're, again, going between two heat sources, and we're going in this direction, this is our Q cold and this is our Q hot, and we're putting work in. If there's the same two heat sources, then they will have the same coefficient of performance. Okay, so we're going to talk about irreversibilities here, and next we're going to be talking about the Kelvin scale and how we use this with getting the Kelvin temperatures.